Hey, hello, Physics 102 students. I got a question here about Chapter 18 as people are getting ready for the exam. It's problem number 20. But before I read the question, let me expand something bigger. This chapter, Chapter 18, has to do with our lenses. The whole chapter is on refraction, and the previous chapter was on reflection. So Chapter 17 is reflection, Chapter 18 is refraction. And in those, we looked at lenses and mirrors. So in this chapter, we're looking at lenses. And the last one, we're looking at mirrors. And as you get ready for the exam, let me do some screenshots here of the video lecture. And so in Chapter 18, and it looks like, you might not be able to read it there. I'm going to bring it to close to the camera. I can't even read it myself. Is that 9? Let's see if I can get it even in the camera there. Is that 9:29 seconds into, looks like day 15, lecture 2, part 3 of 3. But what I did was I said that let's draw these rays. And so without taking too much time in this video solution, but encouraging you to go back and look at the video lecture, this is the convex lens, and it has a focal point, and we put an object out here greater than the focal point. And we said then we can look at some sets of triangles, and it's probably hard to see in this little printout, but this was a blue set, and this was a green set. And then we worked out some equations, which we wrote in blue. And so the height of the image is to the object as the focal length is to the object distance minus the focal length. And then in the green triangles, we came up with this relationship. Now, since this isn't important for this problem, but I think it's important for you to reviewing for the test, I wanted to point out then that what I said was this equation, you want to write it down and have it ready for the exam. So have this ready for the exam. And when would you use it? Well, you would use it if you had a convex lens where your object distance is greater than the focal length. And so that was our argument here. Now, we also said this was identical to the concave mirror. And so that's how I'm trying to tie these two chapters together. So if you have a problem where you have either a lens or a mirror, and the lens is convex, or the mirror is concave, and the object distance is greater than the focal length, this is the mathematical connection between object height, image height, focal length, object distance, image distance, okay? Now, if I read this problem, Chapter 18, number 20, it starts off by saying, where is the image of an object that is located at the focal point of a diverging lens? Okay, so this, the convex lens, is a converging lens. So this was just a nice review and hopefully useful getting ready for the exam, because you never know what you're going to see on the exam. But it's not going to help me for this problem. So I'm gonna put this off to the side. I don't want that one. Let's look at another screenshot a little bit later in the video. It looks like about 16 minutes, or this one here is 15 minutes and 30 seconds, 16 minutes and 19 seconds. Again, it's day 15, lecture 2, part 3 of 3. So same lecture, and I'm still working with the convex lens, but this time I did something a little different, and so I'll put here convex lens. And this time the object is closer than the focal point. And again, not to repeat the lecture, but if you go back and look at it, there's this set of triangles here, which I'll call the blue triangles, or was this the blue? So many on top of each other. I think this is the green one, and this is the blue one. Actually, focal length plus image distance. Green one, yeah. So this would be the green one, and this would be the blue one. But again, without repeating the math, this is the mathematical equation we came up with. Now, let me grab that one I put off to the side. You can see there is a slight difference. Not much. It looks like the blue equation is the negative of it switched. And the green, well, the green equation's also changed a little bit. So maybe there's two changes there. Maybe I shouldn't point out the changes, but just point out that you should write this down. And you should ask yourself, when you see a problem, do you have a convex lens? Now remember, the convex lens is the same as the concave mirror. Okay. And object less than the focal length. And so just ask yourself, what do you have in this problem? Because if it fits this criteria, you're going to want to use this set of equations. And like I said earlier, if we were greater than the focal length, we would fit this condition. All right? So slightly different set of equations when the object is closer than the focal length. But remember, this is for the convex lens and the concave mirror. But if I go back to this particular problem, problem number 20, and again, I'll just read it. It says here, where is the image of an object that is located at the focal length of a diverging lens? Now, a diverging lens is the concave lens. So this doesn't apply. All right, so that's our second scenario. Now, there's only 3 scenarios, so this last one should fit. And so again, I did some screenshots a little later. Actually, later in the video is when we ran out of time and I directed you back to the mirror. So I've got a screenshot that goes all the way back to day 15, lecture 1, part 3 of 4, and it's at 27:55. And this is clearly stating for the convex mirror, which is also true for then the concave lens. Now, fortunately, there's not 2 scenarios like they were for the concave mirror / convex lens, where we had to go, okay, which scenario do we have? Do we have the object greater than the focal length, or do we have the object within the focal length? This one is a little bit easier in the sense that there's only one equation. So you just have to ask yourself when you start the problem, do you have either a convex mirror or a concave lens? So I'll say it again. Let's read the problem. So as I read chapter 18, number 20, it says right away, now it says diverging lens, and so maybe that could be a little bit of a sticky point to realize that the concave lens is also called the diverging lens, but this then is the scenario we would want. Now, I noticed in the video I went ahead and I drew the rays. Well, I didn't do a screenshot of it, but I did not bother to write out the equation. We were out of time, and I just said, hey, go back and look at the convex, and I should add here mirror. And these would be the set of equations. So let me encourage you to then have these ready for the exam. So if I was taking the exam, I would have, this piece of paper right here and say, okay, now if I ever have a convex lens or a concave mirror, I'm going to ask myself, is it less than the focal length? That is the object distance. If it's so, I'm going to use this equation right here. If it's greater than the focal length, okay, then I'll use this equation. Now, if it is the convex mirror or concave lens, I will use this set of equations, no matter where the object distance is. And that's the problem we have. So let's begin the problem now here. Let's write down height of the image is to the height of the object as focal length is to object distance plus focal length. The other equation, height of the image is to the object as focal length minus image distance over focal length. Okay, so there's the set of equations that would be valid for this case, and I know it's valid because it said diverging lens, and we worked this out. Remember, I purposely worked them out, telling you this is one of the hardest things we will do this semester, was that geometry. So I wanted to do it for you. Okay, now, when we drew the lens, well, maybe I should start with the first question. The first question just says, where is the image? So they want to know this. They want to know, image distance. So let me begin with this ratio. Height of the image is to the object. You might call that the magnification. How big is the image compared to the object? And the problem clearly states that the object is located at the focal point. So the object distance is at the focal point. So the bottom becomes f plus f, which is 2f. The f's cancel, and you got 1/2. So you are basically saying the magnification is 1/2. That is, the image is half the size of the object. But where that becomes useful then is we can put that up to here and then solve. So I'll bring this over to here and write it as 1/2 f minus image distance. I'll bring the image distance to the other side. I'll have f then minus 1/2 f and get 1/2 f. So we can answer the first part of this question right here and just say, hey, the image distance is half the focal length. And so if we were drawing a picture, it might look something like this. We would have the two focal lengths for the diverging lens. The object would look like here. The ray going parallel would spread out as if it was coming from this focal point. And the one that's heading towards the far focal point would then go parallel. And so these two would appear to have originated from about right here. And so there it is, half the focal length and half the size. Magnification is half, and it's at a distance of 1/2. All right. Now, maybe I did too much here. I don't know if they're going to ask me to draw the ray diagram. I would just kind of freehand sketched it, but I know this first part is where is it. So you could say it's at half the length, or half the focal length. Okay, now the other part says, is it erect or inverted? Well, you could see kind of in my drawing that it is erect, so it is upright. We also said that this lens always does that. So this lens, and for that matter, the matching mirror, which would be the convex mirror, they always make things smaller and right side up. So this is what I call the boring lens or the boring mirror. It always does the same thing. All right, so that was pretty easy question. Last part, is it magnified or reduced in size? I guess I called this magnification of 1/2, but maybe that's better called a reduction. So it's a reduction, it's 1/2. All right, and that's the three parts to the question. I know I was long-winded, but hopefully that helps you prepare for the exam better.